Hello, I'm Sam Ainsworth, and this is my talk on ParaDox, our new technique designed to improve performance and/or power consumption by replacing the excessive margins on chip supply voltage, which typically waste over 20% of a CPU's power, but are there to avoid errors from variance and unreliable physical properties, with real efficient fault tolerance. Because the latest fault tolerance techniques based around exploiting the parallel nature of fault tolerance are so efficient, there becomes the potential to improve in multiple dimensions of energy, performance, and reliability all at once. So first, why is this now a realistic possibility? Why is the full fault tolerance of today's processors, designed to check for bit flips and incorrect computation caused by cosmic rays or timing errors, now achievable in such an efficient way that it can be more than paid for by a 20% power reduction from voltage margins? Certainly, dual and triple core lockstep, which duplicate all hardware logic and compare the results, are nowhere near efficient enough for such a proposition. But who said we have to run a fault-tolerant redundant copy of a program in the same way as the initial run? Actually, it turns out that error detection is extremely parallel, even for single-threaded applications. We can split up our program into multiple segments, writing the performed loads and stores into a log to be replayed, then executing the results on a much slower, much more energy-efficient checker core. While that part of the code is being checked, we can immediately log the loads and stores of the next part of the program, overlap its checking with the first segment on a different, slow but efficient check core, and so on, and so on. Critically, this type of parallelism doesn't affect coverage. We still repeat all execution, just in a different, more parallel way for the redundant run, and we can combine the results from each separate check using an induction-style analysis. If all segments previous to ours are correct, and our current segment is as well, then the entire program up to this point must have executed without error. We used this property in a paper at DSN 2018 by coupling a standard out-of-order CPU with hardware forwarding logic to duplicate load values to repeat the computation, as well as load addresses and both store values and addresses to check the series operations the program produced. These slices of the program between register checkpoints are repeated on tiny checker cores, adding up to a tiny fraction of the big core's area and power in total. Then, to make the induction process work, we check that the register checkpoints recomputed match the ones taken from the next checkpoint. At DSN 2019, we then extended this error detection scheme to allow it to correct any faults by buffering all store values to allow rollback under the discovery of an error. To make that possible in multicore setups, where the order of rollback and propagation of errors may be unclear, we buffer unchecked stores in the L1 data cache until the timestamp they were executed at is confirmed correct, placing the sphere of replication around the core and L1 data cache. To limit the performance impact of this buffering, we dynamically adjust checkpoint lengths based on eviction and flush attempts in the L1 to adapt the amount of unchecked work. There are more details in those two papers, but the fundamental takeaway is this: via exploiting parallelism in fault-tolerant repetition, we can reduce fault tolerance overheads to be almost negligible on performance and power consumption. That raises an obvious question. If full fault tolerance is now incredibly cheap, how does that impact microarchitectural design more generally? Well, the fundamental unreliability of silicon chips is exacerbated by small feature sizes in today's processors, increasing the variance of transistors and increasing susceptibility to being flipped by even minor changes in voltage. To limit the impact of these, supply voltages have to be set significantly higher than is strictly necessary, and a great deal of circuitry and effort has to be spent on other power-related sources of error, such as voltage spikes. Have we reached the point where the cure is worse than the disease? If this limited form of error mitigation, of over-margining the voltage supply, is so costly, counting for over 20% of the core's energy usage, and full fault tolerance is cheaper, why don't we just go for the latter instead? That way we could undervolt the design to achieve better energy consumption, or overclock it to improve performance, with any errors corrected by the underlying fault tolerance. By adding in fault tolerance, we can turn voltage scaling into the energy trade-off above. Today, we're on the far right, wasting energy through margins. On the far left, if we undervolt too much, then even with underlying fault-tolerant hardware, we'll spend too long correcting our mistakes, and so energy consumption will increase. In the middle, we have our sweet spot, where occasional errors are corrected via ParaMedic rollback, without the rollback itself becoming the dominant performance factor. There's a problem though. We've said that ParaMedic allows cheap fault tolerance, but that's only been tested on devices assumed to be fault-free the vast majority of the time. What we're proposing is to actively seek out these errors and increase their rate through undervolting. Why is it that we'd expect a big performance loss and thus energy consumption increase in the most error-seeking scenarios? Well, to achieve parallelism, ParaMedic deliberately detects errors at a high latency. In the example on screen, we show the computation between two register checkpoints on our main core. We assume an error happens somewhere in the middle, and once we reach the end of this segment, the whole segment is then checked on a checker core. The checker core then checks it much more slowly than the original core executed it, meaning other work, checked by other checkers, is executed on the main core in the meantime. Eventually, the checker core will diverge in some way, as the error won't propagate to this new version. In turn, this will eventually cause some visible state to change, either an incorrect load or store address, store value, or register at the end of a checkpoint. By that point, the error may have affected any future computation up to the point of detection, and so all of the stores that have happened in that time must be rolled back, and all of that computation is wasted and must be rerun. So how much of a concern is this? To work this out and improve on the situation, we used a Gem 5 simulation with a big out-of-order superscalar CPU coupled with a large number of very tiny in-order cores, deliberately chosen to be slow since we can utilize the parallelism for efficiency instead, and over-provisioned to try to limit the performance impact, thus giving us the best potential to actually improve energy delay product. To that, we added a variety of methods of error injection, designed to trigger all of the various ways in which errors can be detected. And as it turns out, at high error rates, this rollback cost is a significant concern. Once errors become very common, we see slowdowns increasing exponentially, reaching up to 16x on the graph above. Ultimately, if errors are relatively common, and the success of each checkpoint depends on the correct execution of thousands of instructions, then forward progress is likely to be limited. Still, knowing that this is a problem, ParaDox, our new scheme, does something about it. In fact, ParaDox gives comparable performance to ParaMedic at around 1.5 orders of magnitude higher errors. If we look at this graph for the compute-bound bit count workload, which has long checkpoints because it doesn't fill the load store long, then we see that 1. Wasted execution is the dominant cost of ParaMedic, wasting over a microsecond of computation for each discovered error. 2. That ParaDox reduces this significantly at high error rates, while leaving the delay and latency high at low error rates to reduce checkpointing frequency and thus overheads. And 3. That ParaDox makes rollback much cheaper as well. In this graph, for the memory-bound stream workload, because it fills up the load store log quickly, it wastes less computation from errors than bit count does, and rollback constitutes a larger proportion of the cost of an error. But we still see that ParaDox's new features limit the overheads. So what have we done to limit these two costs? The first thing is that we adapt the amount of work left unchecked based on the amount of errors recently observed. The critical observation is that if the errors are frequent and all computation within the same checkpoint as or after an error has to be thrown away, and that the latency of detection is based around how many other instructions are in a checkpoint, then the multiple groups of instructions that we all check in parallel should each be smaller, even though this means we need to take copies of the register file either side of each checkpoint more frequently, slowing down the main core. In the baseline ParaMedic, not every element of the load store log entry is filled. We can split the entries into those that have been read and checked, those that the checker core has yet to reach, and those that are entirely empty. The reason some may be empty is that maximum rollback times are already limited by a 5000 instruction timeout, which immediately triggers a checkpoint and checker core execution once it's reached, even if a load segment isn't full. ParaDox dynamically adjusts this based on the observed errors using an additive increase multiplicative decrease technique. If we observe an error, then when we restart execution, our next attempt halves the number of instructions attempted in the next checkpoint. Then, when this new 2500 length checkpoint is checked, if we see another error, it is halved again to 1250 instructions. Otherwise, it's increased slightly to 2510 instructions, and so on, to dynamically reach a steady state that balances the expected number of instructions we can execute with a high likelihood that none of those instructions in a segment are affected by an error and thus has to be rolled back. This is similar to the strategy used by TCP, the network protocol, to set speeds, and is also used by ParaMedic and ParaDox to adapt to multicore communication delays. Still, when our errors are caused by undervolting, adjusting the checkpoint length is not the only way of controlling the amount of wasted work. We can dynamically adjust the voltage to match the error characteristics of both a given application and a given manufactured chip. We thus aggressively optimize voltage, as shown above for bit count, by decreasing it slowly in error-free times, then increasing it in response to error, smoothing out the physical limitations over rapidly changing voltages by adjusting clock frequency over short timescales until the full voltage switch can be achieved. Since error rates are approximately exponential with respect to voltage in practice, we want to achieve a low but non-zero error rate, and so we spend the vast majority of the time below a point when errors are probabilistically feasible but rare. We also alter the load store log, used to replay and roll back memory operations, to make rollback quicker. This is done by both separating out the detection load and store metadata on the left above from the old rollback values shown on the right, needed to correct any errors and restart execution, and by storing the latter as cached lines rather than individual words. ParaMedic stores old writes a word at a time, and has no way of working out whether a word has previously been written to within a checkpoint. This means it has to take a copy of the old data every time a word is overwritten, even if this happens multiple times within a single checkpoint, and has to then repeat these in reverse order for a rollback. ParaDox instead uses spatial and temporal locality to simplify the process. Since we already have to store checkpoint timestamps in the cache to ensure correct multicore propagation, we can work out whether an entire line has been written to or not within the current checkpoint. If not, then a copy of the cache line is taken along with its ECC bits. If the line has already been written to in this checkpoint, as in the new example above, then we don't need to add anything else to the rollback log, only needing a copy of the newly stored value and its address for detection purposes. This temporal and spatial assumption reduces the number of cache line writes on a rollback, and also removes any ordering constraints within a checkpoint on the order of rollbacks, as it guarantees any line will only need to be written to once. Another observation is that while we couple a main core with a large number of very slow checker cores, their utilization is actually very low. Above, we see the utilization of each of the 16 checker cores in our evaluation over SPEC CPU 2006, with wake rate for each being the green fraction of the yellow total. While the worst case uses many of these checker cores, as the execution behavior of the big and little cores is very different, the typical case uses very few of them. While this could perhaps be solved by using less efficient, slightly bigger cores to do the checking, or by designing the checker cores to better match the best case performance of the main core, we can also reduce the typical power demands by power gating. To enable that, instead of allocating the checker cores round robin, we instead allocate the lowest ID available checker core and load store log partition when recording loads and stores from the main core. In this example, we are actively computing on 4 checker cores, the 4th, 0th, 1st, and 3rd in that order 0 indexed, using a linked list to keep track of the original program order, while filling the 2nd, which is waiting for its log to fill before checking execution begins, and we have the final 2 power gated off, along with their load store logs and private instruction caches. So these new changes are primarily designed to seek errors through undervolting, reduce the wasted computation and cost of rollback when errors do happen, and through trying to limit power consumption to give us a better chance on improving on the power budget saved by undervolting. So where do the performance overheads from our redundancy come from? For detection only, this is mainly caused by a combination of the main core being stalled when registered checkpoints are taken, and by all of the checker cores in combination still being unable to keep up with the main core in rare circumstances. For ParaMedic's error correction, the main addition to this is that the buffering of state in the L1, necessary for correct multicore rollback, harms performance under conflict misses such as in SCHEG and A*. Finally, the extra in ParaDox is primarily caused by its dynamic voltage scaling technique causing actual errors to appear that are actually rolled back, unlike the other two where errors are assumed to be negligible in performance impact and effectively never happen. In addition, the new cache line rollback method has varying effects depending on the amount of temporal and spatial locality in the workload. Still, we see that the performance overhead is under 5% on average. The checker cores themselves never add more than 5% extra power consumption averaged over the whole run of each application, and so once the scale of undervolting possible on modern cores is taken into account, the power savings overall of ParaDox stand at 22%. Though these slowdowns on some workloads, which quadratically affect the energy delay product, mean that the EDP win is not always net positive, the geomean saving on energy delay product is 15%. Alternatively, if we increased clock frequency to counteract the slowdown, we would still save 15% on energy consumption. And if we were instead to overclock the design to improve performance, we could increase clock frequency by 13% while using a small undervolt to keep power consumption constant with the baseline and correct any observed errors. In effect, regardless of whether you're seeking energy efficiency, performance, or some balance, the combination of ParaDox and undervolting is likely to be a net win. So that's a brief introduction to ParaDox. What is the moral of this story? In effect, we think that today's voltage margins are too big to remain the solution for keeping hardware running, and that the potential savings make new techniques a necessity and inevitability. Instead, we think that a better consideration of fault-tolerant designs and trade-offs in the space of reliability and performance are likely to allow improvements along multiple dimensions at once. ParaDox is one such solution, and we expect there to be others in this design space. Thank you for listening, and if you have any questions, please email us at the addresses above, Thank you very much.